A continuing theme thus far has been the relationship between the frequency of a value in a population and the probability of that value occurring. We have seen this on histograms and probability frequency distributions. We saw that the area under the curve of a probability histogram, or a frequency distribution, was in fact the probability of that event or range of events. All this comes from the very definition of probability. Probability is quite simply the probability of x is equal to the number of ways to get x divided by the total number of possible outcomes of the experiment. We will never get very far from this basic principle. As a reminder, we posed the experiment that we flip a coin 3 times, and we defined the random variable to be x equal number of heads. Therefore, the random variable could take on the values of x equals 1, or 2, or 3, or 0. Okay? From this, we developed the sample space and wrote down all of the possible outcomes and found there were 8 of these. The sample space is equal to head, 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 tail, head, tail, head, and tail, head, head, and tail, 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 head, tail, head, tail, and head, tail, tail. That's the sample space for flipping 3 coins. To calculate the probability that you got x equals 0, no heads, we would say that the probability that x is equal to 0 is equal to the number of ways that we have no heads, and there's only one of those, and we divide it by these 8 possibilities. That is, in fact, the solution to this particular problem. Okay? Now, if we take the sample space, here's the sample space, and we take this calculation, if you want to call it a calculation, and there's our answer. Okay? Or the probability of flipping 3 times and never getting ahead is 1/8. All this is easy because we can write down all the possible outcomes. There are only 8 of them, and they're not too hard to keep track of. But imagine you want to count the number of unique 5-card hands you can get from 52-card deck by writing down each and every one of the possibilities. We really do need another way to count these without writing each possibility down. The sample space is just too big. And we're in luck. We have the combinatorial formula. Historians of mathematics debate over just how long we have understood these counting subsets. But certainly it has been since 900 AD, although the most careful work is attributed to Blaise Pascal from the mid-1600s. On a side note, the roulette wheel is also attributed to this genius philosopher and scientist and mathematician Blaise Pascal. Let's take an easy case to start. The number of unique 2-card hands we can get from 4 cards. As an example, this could be the total number of unique ways to draw 2 aces from 4 aces in a deck of cards. Remember, we're just counting unique subsets, not probability, not yet. The possibilities are as follows. Okay? Again, the sample space is equal to, and now what we're going to have here is we're going to have the spade and heart, ace, followed by spade and club, ace, followed by spade and diamond, ace. And then we're going to have the, losing track here, heart and diamond space, followed by heart and club and diamond. Okay? Those are all the possible ways you can take 4 aces and combine them in unique subsets. Okay? 1, 2, 3, 4, 5, 6. So there's 6 of these. Now, the real beauty here of the combinatorial formula is it will answer this question, and it'll do it in a very straightforward way. The combinatorial formula is n combinatorial x. Notice that I'm saying n combinatorial x, not n divided by x. There is no horizontal line here. Okay? Another way of saying this is n items taken x at a time, or in shorthand, n choose x. The mathematical expression, n combinatorial x, is expanded as follows. It's n factorial, that's an exclamation point, divided by x factorial times n minus x factorial. And be careful here. N minus x, you have to first take the subtraction and then do the factorial in order to get that. Now, factorial is a mathematical operator. It tells us the following. Let's say that we have 4 factorial. Okay? The factorial says that we're supposed to take every number from 1 to that number and multiply them times each other. So 4 factorial is equal to 1 times 2 times 3 times 4, and that, of course, is 12 times 2, and that's 24. So here is what the factorial operator tells us to do. And by the way, by definition, 0 factorial is equal to 1. Now we can find out whether or not we've got this right. N, in this case here, is 4. So we have 4 factorial divided by x. We're taking them 2 at a time. So that's going to be 2 factorial times 4 minus 2. And again, notice the parenthesis, factorial. And then we're going to get this out here, and we're going to get 4 factorial over that. And sure enough, we're going to get 6. How do I know that? 4 factorial is 1 times 2 times 3 times 4 divided by 1 times 2. This is 2 minus 4. So that's going to be 1 times 2. 2 times 2 is 4. That cancels 4. 2 times 3 is 6. And we now see that this formula will do the counting for us of the unique number of subsets of size x that can be created from n unique elements. This is the same we found when we're writing down all the possibilities. It is important that we remember that we're talking about unordered subsets, because that's what we need for our calculating probabilities. The order of the cards doesn't matter. Okay? Ordered subsets, by the way, are called permutations, and yes, there's a formula for that too, but we do not need it for probability. Just so you are assured that this is a better, faster, and more reliable way to count possibilities, I will tell you that the number of unique 5-card hands that you can get from a 52-card deck, which would be, of course, 52 combinatorial 5, that number happens to be 2,598,960. And the idea that we would actually sit down and find and count and write down the sample space of 2.5 million, of course, is absurd.